That right, Dr. Tiwari?
Yeah,
Yeah.
it's
All right. Yeah. Yeah. All right. Perfect. Okay. Good morning, everyone. Thank you so much for joining this event that we are hosting here. We have Dr. Giulia Marasco with us today, and she will be talking about some of her work on next generation infrastructure assessment, specifically with the use of AI for SHM. A bit of background on Giulia. Dr. Marasco is a postdoc currently at the Department of Civil and Environmental Engineering at Lehigh University. She obtained her PhD in Civil and Environmental Engineering in 2022 from Politecnico di Torino in Italy. Her work lies at the intersection of structural engineering, data science, and artificial intelligence, with main core focus on structural health monitoring. And she aims to create a next generation of digital diagnostic tools for monitoring and maintaining the health of critical infrastructure elements such as bridges, tunnels, etc. A couple of pointers. If you have any questions during or after the presentation, please leave them in the chat window. And once the presentation is finished, Dr. Marasco will be able to answer all your questions. And with that, Dr. Marasco, over to you.
Thank you. Thank you, Debashi, for this introduction, and thank you very much for this opportunity. Today, I'm going to present my research focused on structural health monitoring methodologies based on artificial intelligence. The idea is to provide infrastructure owners and transportation planners with tools for widespread evaluation of their infrastructure assets to enable optimized and smart decision-making about maintenance and management. Before to illustrate the current research, the gap at the state of the art and the future direction in the field, let's start with a brief introduction about the motivation behind this work. The control of structural condition of critical civil infrastructure facilities such as bridge is crucial to ensure safety and to shun great waste of economic resources. Traditional visual inspection are costly, prone to considerable errors, and limited to inspected location and times. To overcome such a limitation, structural monitoring strategies driven by data and AI algorithm has to be developed to achieve high precision solution, low damage detection time, and real-time assessment. The evaluation of structural condition can be performed both as damage detection, if a damage exists, or evaluating the remaining useful life when the structure is fully functional. Structural monitoring methodologies based on AI for damage detection are focused basically on recognition of damage patterns in data. On the other hand, structural health monitoring methodologies based on AI for life cycle assessment focus on the creation of virtual sensors to obtain data useful for the evaluation of the remaining useful life of a structure, such as, for example, train signals. To extend the range of applicability of damage detection and life cycle assessment techniques, a cutting-edge approach involves the use of transfer learning. The idea is to use the knowledge acquired on one specific structural system to evaluate other different but similar systems. Let's start with the two case studies showing how AI can help recognize patterns and identify damages. The choice to show two different structures characterized by different material, different structural schemes, and different service class is done to highlight how AI can help in achieving specific assessment needs. The first case study is the Marchetti Viaduct, a steel arch suspended highway bridge in Italy. For the evaluation of its dynamic behavior, we analyzed the acceleration data acquired at 4 points of the bridge. The use of operational model analysis techniques by means of data-driven stochastic subspace identification algorithm allowed the extraction not only of the structural dynamic characteristics, namely the natural frequencies, the damping ratio, and mode shapes, but also the estimation of the uncertainty associated with them. Clearly, there are two main factors that influence the range of scattering of the results and their uncertainties. The first one is the volume of data, and the second one is the temperature. Traditional approaches for damage detection create a statistic distribution of the dynamic parameters in a healthy structural condition, defining a range of acceptable parameters and identifying as anomalous data outside this range. Here, I focus instead on the development of an AI damage pattern recognition strategy. This AI strategy is based on the k-means algorithm. The traditional k-means method allows the analysis of collected signals with the distinction of two classes representing the undamaged and the damaged state. This can provide a photograph of the structural condition, but it prevents the monitoring of structural changes over time, and also the potential progression of damage from early stage to a critical size. Here, I present a process able to monitor the structural changes. After the training to create the cluster representing the healthy condition, new signals are evaluated. This process considers the distance of the signal to the centroid of the healthy cluster and evaluate the damage evolution. To monitor the evolution of the damage level, the process calculated the optimal number of clusters by means of literature criteria when critical time units are reached. To quantify the sensitivity of this approach in identifying damage, 3 potential damage states have been simulated imposing variation in the acceleration signals. The 3 criteria were used to analyze data covering all the 3 damage levels, so LD7, 8, and 9, and to test the ability to recognize the increase in damage severity, calculating the optimal key, so the optimal number of clusters. As can be seen, a change in the optimal value is displayed for all the 3 units by the gap criterion. In addition to the capacity to recognize an increment of the damage severity, such a methodology has shown better results for the damage detection capacity with respect to the traditional approach. Now, can we move to the second case study, the Olio Viaduct in Italy? It is a simply supported pressurized concrete railway bridge. Even in this case, the goal is to use dynamic measurements to evaluate the behavior of the bridge under environmental conditions and to issue warnings for abnormal values of recorded parameters. But here we are specifically interested in the evaluation of the strain state of the deck, fundamental to investigating the presence of potential cracks or pretension losses, and in the assessment of pier rotation and joint expansion. The data used to develop the proposed control strategies are related to sensor placed in 2 specific meaningful sections, the midspan and the support. The sensors are reported in the table and are of different types. There are thermometers, strain gauges, clinometer, and biaxial support displacement. The data are analyzed using a reconstruction-based approach. The method is based on training deep learning regression models on a dataset related to a healthy condition in order to determine the correlation between input and output parameters. The development of physical models in this case was set aside, and a black box system identification approach was preferred due to a complex relationship among the parameters. Machine learning algorithms, in particular multi-layer perceptron and gradient boosting machine, revealed very efficient. With this strategy, 2 tasks were faced. The first one is the assessment of the midspan strain of the unloaded deck, and the second one is the assessment of pier rotation and joint expansion. Here, for the sake of brief, only the first will be described. The methodology is composed by 3 steps: the model training, the validation, and the test. Each step, before and after the use of machine learning algorithms, involves the use of pre and post-processing operations. They consist of a z-score normalization techniques and an inverse z-score normalization with regard to a moving time window. In this way, the limitation of this core technique associated with its exclusive use with the stationary series is overcome, and it is possible to give repetitiveness to data and allow a successful training of the machine learning algorithm. Such operations are pivotal due to the fact that most structural quantities time series are not stationary, and this behavior is amplified for specific materials, such as concrete, which show delayed phenomena, like, for example, the creep. After the training of the machine learning algorithm, the models are validated using another set of data for the undamaged structure, and it is possible to create the healthy error range. The residual is calculated as the difference between the measure and predicted outputs, and it has a Gaussian distribution with a mean, mu, and a standard deviation, sigma. The threshold for the healthy error range can be defined by means of the controlling parameter key. At this point, signal affected by damage can be tested. I propose a damage index like the moving median with respect to the 7 preceding days. Because if the residual had been used as a damage index, as in the standard signal reconstruction approach, there would be a lot of false positive. As already mentioned, the evaluation of the strain state of the deck is fundamental to prevent some structural problems. Indeed, the deformations are the mirror of potential cracks or pretension losses. Here we exploited the parameters to develop the correlation model in an undamaged condition, where the ones are the ones recorded in the midspan section. 3 types of input can be distinguished: the raw, the processed, and the additional input. The term raw points out the reading at the sensor without any elaboration. So, for example, we can refer to the air temperature. The term processed instead is used for the input obtained after the processing of several raw inputs. So we can consider, for example, in this case, the mean of the temperature or the gradient along the the height of the cross section. The term additional instead is used for features not directly linked to the reading at the sensor. In detail, the reference is made to additional temporal features indicating the hour of the day and the week of the year in which the parameters were recorded. To feed the model with this information, we encoded those features using sine and cosine function of the values, so to ensure time data continuity and periodicity. For the output of the system, only raw outputs have been utilized, and we use the strain. The best AI model in this case is an extreme gradient boosting machine with decision trees with a maximum depth of 6 and a learning rate of 0.3. Simulated anomalies were adopted to assess the damage identification capacity. They were simulated imposing a given offset in sensor values. This offset starts from 0 and increases linearly in time up to the given value in 3 different time spans: 106.8 hours, 336 hours, and 720 hours. The reliability of the proposed strategies has been tested by varying the starting point of the anomaly, and 50 points belong to the test anomaly set were considered. Here there is an illustrative example. The anomaly plot shows the application of an anomaly by means of the imposition of an offset equal to 10 microstrain achieved in 168 hours. On the other hand, the residual plot displays the trend of the residual, that is the red line, the damage index, the median, and the healthy condition error rand, the orange band, limited by the UCT threshold. The value of key to define the extremes of normality range has been set equal to 2. In the residual graph, the blue dashed line indicates the identification of the anomaly. Here, the damage index falls beyond the control limit of the healthy condition error range, and the tables synthesize the results in terms of detected anomalies as function of their amplitude and of the time span. The method successfully captures anomalies representing approximately 5% of the average signal value. Obviously, very small anomalies that evolve in a wide time span are very difficult to be detected. Beyond the ability to capture anomaly, it is important to note the complete absence of false positive. The ability of the damage condition-based threshold turned out to be greater with respect to the design-based threshold in detection of early-stage anomalies. These latter are established based on consideration resulting from the expected structural response. The design alert value is equal to the 100% of the calculation value based on the maximum stresses obtained in the service phase. The alarm values are equal to 120% of this limit value. So the figures show a comparison between the two approaches and highlight the better behavior of the damage condition threshold. Thus, the data-driven approach results more effective. As illustrated so far, structural health monitoring methodologies exploring AI for damage detection provide promising results. But there are two main gaps. First of all, to be successfully, they require large data volumes that are often lacking in the real world. Then they are typically able to identify and localize damage, but rarely can estimate its severity. Therefore, we have to find solutions to overcome such gaps. To this aim, we can consider cutting-edge sensing technologies and optimized techniques. To easily acquire huge amount of data, we can consider the use of mobile sensors. These allow unprecedented data volume and increased time and space monitoring resolution at a low cost. My research team proposed a complete system identification strategies using acceleration data from a limited number of simultaneous sensors on the structure. These strategies that I shall not describe in detail here for time limitation reason, use smartphone application for synchronized measurement and a spatial frequency content aggregation approach to directly connect mobile measurement to traditional system identification techniques. The results are very promising, but there are still challenges to be addressed. Among them, future plan involve the investigation of vehicle-bridge interaction, the analysis of the impact of vehicle dynamics and road profile. To overcome the second gap, namely to achieve the capacity of estimating the damage severity, we can consider the use of optimization techniques. The question is, how can we tackle damage severity estimation as an inverse problem using priori damage identification and localization information? The solution can be found in the use of genetic algorithms. The genetic algorithm is an optimization techniques based on Darwinian principles that allow the generation of good solutions starting from a population of individuals that evolves over time. After defining a set of possible solutions, namely a population of n individuals, each solution is evaluated using a cost function. By using crossover and mutation operators, the better individuals are chosen to create new individuals, namely the offspring. Then, individuals merge and sort operations are performed. The new generation will be made up of the better N individuals. When the specified number of iterations is reached or the quality of the better solution is considered acceptable, the process is complete. In a damage severity estimation framework, individuals can be, for example, the bending stiffness of the elements identified as damaged by previous analysis. In one of the applications for damage severity estimation in bridges that I developed, the cost function for the genetic algorithm uses displacement at midspan and the rotation at the supports as monitor parameters, and it is the sum of 5 contributions. The power coefficients, highlighted in red, are introduced to weight each atom. This is just an example, but other parameters coming from dynamic characteristics can be used. In this specific case, the third and the fourth terms are directly linked to the recorded measurements. On the other hand, the first term stems from the displacement of other structural nodes, which are estimated via the Wurpilot algorithm, and instead the last term is based on the ratio between the rotation. In this specific subscript M and A denotes measure and analytical quantities respectively. The measured values were numerically simulated using a FEM analysis, with the damaged elements having reduced bending stiffness. In the real-world application, they should come from on-site measurements. The analytical quantities, on the other hand, were determined using a FEM analysis in which the values of bending stiffness of the damaged elements were picked up from the genetic algorithm individuals. To reach a high accuracy of the estimated variables, a proper coefficient for each part of the cost function is used. For this reason, a neural network associating specific power coefficient to a specific damage case, namely a specific location of damage, is adopted. To this aim, numerical simulations were carried out to associate the damage scenarios characterized by some damage elements with the power coefficients. The minimum and the maximum value of the investigated variability range for each power coefficient were set to 0.1 and 1, respectively. This procedure has been tested by means of damage cases stipulated by a finite element method representing the Olio viaduct, the viaduct described before. The error distribution in the estimation of the damage severity has a normal distribution with a mean of 0.01 and a standard deviation of 0.06 that indicates that about 70% of the damage cases have an error less than 6%. For this reason, the findings are thus considered satisfactory. Let us now move on the second aspect of the structural assessment process, namely the evaluation of the remaining useful life. The traditional approach uses the stress cycle counting methods, which is based on recorded stress or strain time history and rainflow diagrams. But measuring strain signals carries certain challenges, for example, the accessibility to critical location, measurement errors, and high labor costs. Recent development in artificial intelligence have facilitated the development of efficient data-driven schemes, creating virtual sensors. AI algorithm can produce, indeed, strain signals starting from acceleration signals that are more convenient to record and can be an alternative to real sensors. Over the year, advanced deep learning architecture showed good results. One of the most comprehensive studies in this field has been done by my research group on the Jean Hartzell Memorial Bridge. A complex architecture composed by convolutional neural networks and transformers showed good results in terms of accuracy and interpretation of the network. Nevertheless, there is room for improvement due to the fact that this model is driven only by data. To this aim, the focus is currently on the development of graph neural networks to move from traditional algorithms that behave like black boxes to physics-based artificial neural networks. At this stage of the research, to investigate the impact that physics information can have on the problem at hand, data from a numerical model are used. Future plans involve the use of data from real-world case studies and the use of acceleration data from mobile sensors. The idea that data can be organized as a graph composed of nodes and edges was introduced in other fields. The majority of studies using graph neural networks are, for example, in medicine, system recommendation, and traffic prediction fields. And this is due to the fact that there are data originally structured as graph. We can think, for example, to molecules. Although few applications are in the structural engineering field, the use of this concept at the structural level is very promising, because by expressing the structure as a graph, the model can capture spatial properties and element connection, thereby improving the model's understanding of structural response. I'm going to show an investigation of the performance of a graph convolutional network converting acceleration signal to a strain signal at each structural node of the simulated beam in a supervised learning approach, evaluating the impact of physics information within this architecture. A graph is typically represented by the equation 1, where V are the nodes, E the edge, and A the adjacency matrix. In the structural case, the nodes symbolize the structural joint, and the edge are the structural components linking the joints. Two key matrices define a graph, the feature matrix and the adjacency matrix. The first one contains the attributes of the nodes. On the other hand, the second one contains the information about the node connection. Among the various types of graph neural networks, this study specifically concentrates on graph convolutional networks. This type of architecture aggregates node information from neighboring nodes using convolutional techniques and allows the obtaining of a good balance between accuracy and computational cost. Equation 2 shows the convolutional operation in which the node representation at layer L plus 1 is calculated starting from the node representation at layer L. The graph convolutional network architecture consists of several key components. The first part containing the graph convolutional layer compresses the input sides to capture the most crucial feature within the acceleration signal. Following this, the model comes back to the original size to make predictions for the strain signals. The model training utilized a common Adam optimizer. However, the primary focus of this study is not on optimizing the model, but rather on demonstrating its applicability and the benefits we can obtain introducing physics information. At the end, for the evaluation, we use the time response assurance criterion as a metric to assess and compare the approaches. To incorporate the physics information, both the feature and the adjacency matrices have been used. Parameters related to the geometry of the structure, the boundary condition, and the structural dynamics have been incorporated. As regards the geometry, nodes coordinates and structural member length information have been used. As regards the boundary condition, indexes related to the structural area to which each nodes belong that indirectly carry this information have been integrated. And finally, as regards the dynamic of the structure, we use the mode shape. Starting from a traditional adjacency matrix composed of elements that are set equal to 1 if the nodes are connected and 0 otherwise, this study investigates how the results are influenced by the introduction of physics information into the future matrix. The classical future matrix contains the attributes of the node, but moving from the scenario 1 to 2, the matrix is expanded by means of concatenation to consider an increasing amount of physics information. In this first scenario, node coordinates and the normalized value of the first mode shape are incorporated. In the second scenario, additional information specifying the structural area of the node is included. What can be observed from the track distribution, introducing additional physics-related information has had a positive effect on the overall performance. Afterward, we focus on the introduction of physics information also within the adjacency matrix. As shown, each structural system can be described using the eigenvalue decomposition approach by use of mode shapes and corresponding natural frequencies. The higher the difference in mode shape across nodes, the lower the spatial correlation. We use equation 3 to calculate the values of a weighted adjacency matrix. In this formulation, we consider the first 3 modes with the associated periods T and normalized mode shapes. In the scenario 3, the overall trend demonstrates improvement. In the figure, for example, the green line describing the S3 distribution is situated below the blue line that represented the second scenario on the left side and above it on the right side. Furthermore, the positive kurtosis value in the scenario 3 indicates a distribution characterized by a distinct peak. Afterward, we consider introducing another significant physical parameter affecting signal similarity between nodes, namely the distance separating them. The higher the distance across nodes, the lower the spatial correlation. The 3 curves correspond to 3 different values of n that show a narrowing of the distribution with respect to scenario 2 and 3. And these allow to remove outliers. By now, I illustrate structural monitoring methodologies based on artificial intelligence related to a specific structure. Recently, the concept of population-based SHM is revolutionizing the field, offering a solution to assess several similar breeds, exploring long-term data from only one breed. Domain adaptation techniques like transfer component analysis have gained attention in population-based structural health monitoring for enabling knowledge transfer within clusters of similar structures. PCA is a complex mathematical algorithm that minimizes the difference between the probability density distribution of the source and target bridge, enabling in this way the transfer of knowledge. To design a transfer learning approach, we need to answer 3 main questions. First of all, we have to understand when we can transfer knowledge, then what we have to transfer and in which way. We can transfer knowledge among similar structural scheme, with a similar material, and subjected under a similar environment and operational condition. We transfer damage-sensitive feature, in our case, the natural frequency, and in the case of domain adaptation techniques, we use a feature-based transfer learning approach. The most important concept in a transfer learning context is the one of similarity. The success of unsupervised transfer learning for damage detection is influenced by three key factors. The physical dissimilarity related to geometrics and material factors, the dispersion of the future that can be partially corrected with the normalization, and the magnitude of damage. To define the concept of similarity and avoid the negative transfer, a numerical study is carried out using two simply supported beams with the same cross-section but different lengths. One represents the source domain and the other the target domain. The parameter delta varies from minus 0.2 to 0.2 instead of 0.1, and the natural frequency in our case are assumed to be the damage-sensitive features. To build the source and the target dataset, Gaussian distribution of the three key structural parameters, the modulus of Young, the height, and the width of the cross section for three different dispersion scenarios, combination 1, 2, and 3 are generated. This distribution have a mean value reported in the table here in the left corner of the slide, and a standard deviation obtained by multiplying the mean value of the parameter by a dispersion coefficient related to each dispersion scenarios. After the Gaussian distribution are created for the three dispersion scenarios, 1,000 samples observation are randomly collected for the source and 300 for the target beams. To calculate the natural frequencies for the undamaged condition, the formulation here reported have been used. To simulate damage cases for the target domain, a crack is introduced and 20 natural frequencies observation are obtained for three damage magnitude scenarios, labeled according to the average depth of the crack. We use the S10 for a crack depth, for example, of 10 centimeters. The cracks are located in the same area of the beam, but the exact position is chosen randomly between the 1 meter that represent the 20% of the length and 1.2 meter that represent almost the 25% of the length from the left support. The longitudinal bending damage frequency is computed using an analytical formulation proposed by Loya. The approach considers a beam with a crack crack length of A, located at a distance L stars from the left support. Because of the absence of analytical formulation related to flexural, transverse, and torsional modes, a finite element model was developed to able to estimate the variation to be applied to the frequency of the undamaged beam to account for the effect of the crack presence. The flexural, transverse, and torsional mode in damage condition are calculated with the assumption that the ratio between damaged and undamaged transversional and torsional frequency in the FAM model are the same as in the analytical model developed in MATLAB. TCA explored 45 scenarios defined by now because we consider 5 lead differential, 3 dispersion combination, and 3 magnitude of damage. The classification performance is presented for all scenarios in the next slide, but 5 of them are selected for a more detailed description of the findings. The selection is designed to cover meaningful scenarios. The observation here, we report the observation of the source and target beam in the frequency space, namely in the original space. The table summarized the damage detection errors defined as the percent of false positive, here indicated as error 1, and false negative, the error type 2, for all 45 testing cases. For the 5 selected scenarios, here there are also the plot of the data distribution in the latent space. Such technique is full. Here we can see that there is actually an overlapping between the source and the target in the latent space. Such a technique is full capable of recognize the normal behavior of the target structure in all the cases, even if small false positive here are not constant and seems to be influenced by the level of dispersion of the undamaged data. The classification performance instead is highly influenced by the magnitude of damage and by the dispersion of the undamaged target data, especially for the smallest and medium levels of damage. But it is important to underline that this is an issue for all machine learning algorithms, and it is not influenced by the transfer of the knowledge. On the other hand, what is important is that the length differential between the source and the target structure seems to have a very limited impact on the classification performance, which means that transfer learning between structures that are geometrically considerably different is still feasible. PCA has also been tested in a real case study with the 2 pedestrian bridges. Both bridges are in front of the Lusofona campus in Lisbon. A monitoring campaign was conducted on both bridges from November 2021 to March 2022. The measurements were acquired under ambient vibration test using the smartphone application app for SHM. Data damage was artificially simulated to the target bridge with adding mass, as has been shown in this picture. To accomplish it, actually on March 2, 2022, a 45-minute ambient field test was performed on the target bridge in order to obtain additional observation with an added mass capable of slightly affect its modal properties. Assuming an average of 65 kilograms per person, the total additional mass caused by around 50 people on the deck is estimated around 3,000 kilograms. The result show that TCA is able to effectively minimize the difference between the probability density distribution and to ensure, therefore, a good damage detection capacity. To conclude, to summarize, advancing structural health monitoring relies on cutting-edge sensing technology and the integration of physics-informed AI. We need new sensing technology that enable the transition from dedicated network to crowdsourced data, generating big data that improve both the temporal and the spatial resolution of the monitoring information. So we have to use the next generation will use mobile sensing because it provides several advantages over stationary sensing with a higher spatial resolution and fewer sensors. On the other hand, it's very important the use of novel AI approaches that leverage big data from these new sensing technologies to enhance damage diagnostics and improve fatigue life estimation techniques. Among them, we will focus on physics-based AI, so for example, the graph neural network, and on the utilization of transfer learning techniques to ensure scalability across a broad inventories of bridges. Thank you, and I'm pleased to answer any question.
Thank you so much, Giulia. That was a great presentation. Lot of interesting thoughts added in there. So I think this must have been super beneficial for all the attendees. If you have any questions, you can please put them in the chat box and Dr. Marasco can answer the questions. Giulia, can you see the chat?
No, actually, no. Maybe I have to stop the sharing.
Maybe.
Yeah.
Yeah. All right.
Yeah. Sure. Okay. So, is there any isn't working? So, yeah, I'm just reading the question. Is there any recent work in progress in determining seepage? Okay. Okay, so as regard the last question, they ask about doing analysis of mean, what will be the boundary condition. Are you referring to the transfer learning approach? There is a question by Kumar. For doing analysis of mean, what will be the boundary conditions? If it is referring to the transfer learning approach, we use a classical boundary condition to consider simple supported pedestrian bridge, because this was our scope. So actually, I mean, the classical boundary condition.
Yeah, I think Suresh Chakravarti, he sort of rephrased his question about seepage. You may want to address that.
Yeah, I want to know how to determine seepage in RCC structure through SHM techniques. Are you referring about what we consider as built, or because for me it's not clear what is meaning for seepage?
Suresh Chakravarti, if you want to respond to that, please feel free to do that to clarify your question maybe. And Giulia, you can continue with the other questions in the meantime.
Yeah. Then I have a question about how far does the analysis go to providing the solution? Okay. As regard the question about how far does the analysis go to providing the solution to repair weaknesses? Okay. Usually, these systems are able to provide a warning. So depends on the system. If the system is related only to the identification of the damage, then we will need next investigation to understand what is the best repair solution. If the system, for example, as shown with the genetic algorithm, is also able to give information related to the severity of damage, at this point, we have more detailed information, and bridge owners can have more support for the decision makers. Okay, then, sorry, a lot of questions. Do physics-based AI run with a limited data set? Actually, no, in the sense that physics-based artificial neural networks can use a slightly limited database, because they have also the more information. So they are not based only on data, but depend on the complexity of the network, because a very complex network as the one shown with the convolutional neural network and transformers needs a large amount of data, and this is the reason for us to consider the utilization of cutting-edge sensing techniques like mobile sensing, because in any case, even if this model can leverage physics information, if they are very complex, they need huge amount of data. So I go to the next one. How generalized these AI models are? Are they specifically trained for the case study you studied? Okay, so as regard the question about the generalization of the AI models, as illustrated in the first part of the presentation, some of them at this stage are related to a specific case study and they are customized for specific needs. Now I'm working on transfer learning for this scope. So the idea is to make this model scalable and to reuse a model trained on a specific structure for similar structures. So this is the next step for the transfer learning. By now, the only work that transfer knowledge from one bridge to another one use domain adaptation techniques. But the idea is not only to use transfer learning for damage detection, but also for life cycle assessment purpose. So the idea is to make scalable also network like the one for that create virtual sensing, to have the possibility to reuse this network also for similar other similar structure. I can go to the other one. Actually, I want to know the techniques through we can determine simple. Okay, while showing in one slide the beam, in that we can see the visibility of the crack. Okay, maybe for the there is another question about the crack, so the depth of the crack. Maybe in the image was not so clear, but the crack that we consider it's small enough, so it's around 5% of the height of the beam, of the section of the beam. Does this transfer learning approach eliminate the need for damaged data as well? Yes, it does, in the sense that there are different types of transfer learning. Here I talk about an unsupervised transfer learning, so we need only data from an healthy condition. We need a lot of data for the healthy condition for the source domain and few data from the healthy condition of the target domain, but we don't need damaged data because we are talking about an unsupervised transfer learning. The damaged data are needed in supervised approach, like in the common machine learning. It's the same. Okay, so which approach do you recommend for leakage detection in water distribution system? I think that the approach, the best approach has to be customized at this stage on the type of problem. So there is a question about what is the recommended approach for the leakage detection in water distribution system. Actually, from my based on my knowledge, for water distribution system, the approach, the most used approach are the one that exploit machine learning and transfer learning in terms of fine tuning, but with image. So I don't know if I answer specific to this question. What will be the maximum length to analyze the bridge? Okay, if the last question is what will be the maximum length to analyze the bridge? If the question is related to transfer learning approach, the idea in this case was to understand what is the allowed variability in the length to avoid negative transfer. So in this case, we check that a difference of plus or minus 20% is an acceptable variation. Of course, we are talking about two bridges that are structurally similar. So they are both simply supported. They are pre-stressed bridge. So there is the important thing is that we need a similarity among them. then what we can do is investigate what is the variability in the parameters, but we need a basic similarity. I don't know if I skipped for mistake some question.
Yeah, I think you missed the seepage question from Suresh Chakravarti. So I think,
okay.
So I can read it out of you. So he's talking about,
Okay.
he wants to know the techniques through which we can determine seepage in RCC structures, like we find cracks and deformations in structures through SHM. So maybe he's looking for techniques that will help determine seepage specifically in RCC structures.
Okay. To be honest, I don't know how to answer to this question. I don't have a detailed answer.
All right. There's one more question. Yeah.
What will be the maximum? No. What are the loads to be assigned for designing the bridge? Okay. In the for the three application, I consider a bridge under ambient vibration, so I'm not consider a specific load on the bridge. As regard the genetic algorithm, for example, one technique to obtain the parameters is to consider the use of influence line. In that case, due to the fact that I was considering a railway bridge, I simulate the use of loads related to the train that were crossing this bridge. But it is a specific case. In that case, we need to close the bridge to interrupt the activities, the operation of the facility, and we consider, the loads, realistic loads that can cross over the bridge. But the idea, for example, also for the genetic algorithm, is not to use parameters related to the use of a specific load, but to consider parameters that can we extract, for example, from mode shapes, so always under ambient vibration, because this gives us the possibility to don't interrupt the operation of the facility. Okay. There is another one, like to share information on ambient vibration examination in real life case. How effectively can transfer learning reduce computational complexity and data requirement when calibrating AI models with physics-based simulation of dynamic loads, the vibration characteristic in large structure. Okay. So now I am at the question about the information on ambient vibration examination in real life case studies. Okay, as regard the ambient vibration, we usually collect the data for 1 year to allow that this data cover all the change of temperature. Because we are not referring to a specific load, but we need to understand what is the response, what is a complete response to the difference in temperature. So we have to consider the different season. And moving to the second one, always of the same, how effectively can transfer learning reduce computational complexity and data requirement when calibrating AI models with physics? Okay, so the second one is regarding the transfer learning and how these techniques can reduce computational complexity. The idea, transfer learning can be used in 2 different ways, or by means of domain adaptation. So as the last case that I showed, actually, there are some domain adaptation techniques like transfer component analysis that are complex algorithm, but they allow actually the overlapping of the distribution. So the complexity in the use of damage adaptation techniques, the reduce of these complexity is not a complexity related to the algorithm, but is these are very useful to reduce the amount of data. On the other hand, there is the transfer learning used in terms of fine-tuning. Also, in this case, we are able to reduce the amount of data. Usually, fine-tuning techniques are used to the classification of images. In that case, we have both the advantages because we are able to reduce the amount of data for the second system that we have to analyze, but we are also able to reduce the complexity of the algorithm in terms of training, in the sense that very often we can freeze the first part of the models, and we can make just a retraining of the last layers of the models, and in this way we reduce the effort both in the design and in the training, so in the computational time to train this type of network. Then the question is about related to the physics-based simulation of dynamics. Data requirement calibrating. Okay, the other question is related to the calibration of AI models with physics-based simulation of dynamic loads and vibration characteristics in large structure like stadium. Okay, as regards the artificial intelligence model that leverage physics-based information, what happened is that we are able to introduce this information, so in some way incorporate this information. Now, this information can be incorporated by means of different methods. As I show, for example, for the graph neural network, we can incorporate this information by means of some matrices, but usually other type of physics neural network are able to include this information by means of the loss function. In this sense, this type of network, this type of information guide the network to learn fast and better. So the calibration of the models depend on the specific case, what is the network that you want to use, and what is the method in which you want to train the network. I'm going ahead. I wanted to know those don't have sufficient background in programming, how they can learn efficiently and implement it within SHM database. Okay, the other question is related to the capacity of coding, and I mean, for this type of problems, you need to develop a capacity of programming, because otherwise, I mean, it is difficult. This is an interdisciplinary field, and you have to merge both structural engineering skills with data science skills. Then there is how to estimate the improved fatigue of life techniques. Okay. Okay, then there is another question related to how to estimate the improved fatigue of life techniques. Actually, the techniques that I described are only to understand what is the current condition. Then you have to consider other techniques to actually improve the status of the structural condition. The last one.
I think there are many questions from the participants, and we are running over the time. So yeah, probably they can email you more questions. I'm sure you ignited a lot of thoughts in their minds, and they have many questions. So I recommend they can email Dr. Giulia, and I'm sure she will be happy to answer all the emails. Yeah. Right, Dr. Sen?
Yeah, that's absolutely fine. And
yeah, because because
on,
more questions are keep on coming, and we cannot
yeah.
I agree.
Yeah, and I'm sure Dr. Marasco has other meetings to attend to after this. Yeah. So again, thank you so much, Dr. Marasco, for doing this on such short notice, I must add. So really appreciate that, and thoroughly enjoyed your presentation. Yeah.
Thank you very much.
Just for everyone else, we will resume this seminar series again in spring from February. So in the meantime, have fun in the holidays, take care, and enjoy your break. And I'll see you in the new year.
Thank you very much to everyone.
Dr. Tiwari, anything you want to add?
No, I'm good. I'm good. So thank you everyone for joining today, and thanks Julia for joining in a very short notice, to be honest. And I was not expecting that the speakers will be ready very quickly, but thank you again for joining and starting this series. And I'm sure you will keep contributing to the series in the future too. Thank you so much.
Very much. Bye,
Thank you. Bye, everyone. Take care.